Asteroids are leftover debris from the solar system's formation, and they may hold clues to the early history of the sun and planets. NASA's OSIRIS-REx mission will bring a piece of an asteroid back to Earth. What this untouched time capsule from space could reveal about life as we know it. That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast presented by Southwest Research Institute. Hello and welcome to Technology Today. I'm Lisa Pena. Our guest today describes asteroids as time capsules that hold information on the history of our early solar system, with records of organic materials and water that brought about life on our planet. Dr. Vicky Hamilton, an SwRI staff scientist and co-investigator for NASA's OSIRIS-REx mission, is awaiting the collection of a sample from the asteroid Bennu. She joins us from Boulder, Colorado, to tell us all about this exciting mission and what it could mean for humankind. Thanks for joining us, Vicky.
Hi, thanks for having me here.
So let's start with an overview. What is the NASA OSIRIS-REx mission?
Well, at the most simple description, it's a mission that's designed to help us understand our origins by returning a sample of leftover debris from the formation of our solar system. I can kind of build on that by saying that OSIRIS-REx, the name of our mission, is actually an acronym. And that acronym sort of summarizes all of the aspects of what we're trying to do. So we're trying to understand origins. So that's that O in OSIRIS-REx. And then the SI is for spectral interpretation. So that's learning about the composition of the asteroid Bennu. The RI is for resource identification. We want to understand what potential resources exist on asteroids. Then S is for security, and that's actually really interesting because Bennu and some other asteroids are potentially hazardous to us on Earth if they were to hit us. And then the Rex is for regolith explorer, and regolith is just a planetary science word for the ground, the rocks on the surface of Bennu. And so to really complete this mission, our first priority is to collect a sample from this asteroid Bennu. And the reason we want to do that is so that it won't be contaminated by contacting the Earth as a meteorite. We want to map the asteroid and understand it just as part of our solar system. We want to document it to understand where this sample has come from specifically. And then we also want to make some observations that will help us understand whether this asteroid and others will become more or less hazardous over time, and then compare to observations we collect from ground-based telescopes and verify that everything we're interpreting from those ground-based telescopes is really what we see when we actually go up close.
So I think that's really interesting. As you mentioned, we've had meteorites fall to Earth, and we've studied those, but this is different. This is going to be a pristine sample. Why is it so important that this sample be untouched straight from the asteroid?
So usually the way things work is that we have asteroids out flying around in our solar system, just like the planets. And these asteroids are things that didn't get included in planets, and so they are just little pieces of debris. Now, when one of those little pieces of debris flies really close to the Earth or flies directly at the Earth, it usually burns up in our atmosphere, but sometimes it's big enough and it doesn't. And so if the pieces of that asteroid come through our atmosphere and land on the ground, we call those meteorites. So you have to think about how that meteorite got here. It had to go through our atmosphere. Our atmosphere has chemistry that interacts with that meteoroid as it's going through the atmosphere. And so that there's chemical contamination from the atmosphere. And then when that meteorite lands on the ground, It's not just interacting with the atmosphere anymore, it's now exposed to everything in our environment. And we have biology here, we have organic chemistry here. That's you and me and, and the plants and animals and everything. And then we also have water on this planet. And so even if somebody sees a meteorite fall and they go collect it within a few hours, that meteorite has already been contaminated by contacting the water and the organics that are around us all of the time. And there's a great example of a meteorite called Sutter's Mill that was found in California. It was observed to fall. It fell partly in a parking lot. It got parts of it were driven over before people could get out to collect the sample. And there's another meteorite called Tagish Lake that literally fell on a frozen lake in the wintertime. And so, even if you get to them very, very quickly, you can think of every meteorite as already being contaminated. And so we don't want that contamination in our sample. So that's the goal of OSIRIS-REx.
But why is it so important that the sample that you get from Bennu is untouched?
So the reason we want to get a completely pristine sample from the asteroid Bennu is to make sure that what we measure in our laboratories is exactly representative of the earliest solar system. And so to just remind folks, our solar system formed about 4.56 billion years ago. And so the Earth has evolved tremendously since that time, and the chemistry that we have on Earth is very, very different in terms of its current properties relative to what we had at the early solar system. So when a piece of an asteroid falls to Earth and is collected as a meteorite, it's come through our atmosphere, it's sat on the surface of the Earth, and in all of those interactions, it gets contaminated by our atmospheric chemistry, our biological chemistry, our biosphere, us, you, me, the animals, plants. And the water that we have on Earth is not exactly the same chemically as the water in the early solar system. So we can pick up a meteorite as soon as we see it fall, but even then it's already too late. It's already been contaminated just by being on Earth. So if we really want to measure and understand the earliest solar system chemistry, we need to do that with a pristine sample.
So when was the OSIRIS-REx spacecraft launched?
Well, our 4-year anniversary is coming up next week on September 8th. So our launch was September 8th, 2016.
And it went straight to the asteroid and Bennu. So why did you choose to explore that particular asteroid?
Well, so Bennu, I mean, that's actually really a great question, because when we were writing the proposal to fly this mission and sending it to NASA, we had to figure out which asteroid we wanted to go to. And at that time, there were more than 500,000 known asteroids. And so we had to sort of come up with a list of criteria that helped us narrow down which one we wanted to go to. So we knew we wanted one of these near Earth asteroids, an asteroid that has an orbit that crosses the orbit of the Earth and makes it a potential hazard to the Earth. So we wanted one of those. We needed an asteroid that had a particular orbit that would make bringing the spacecraft back to the Earth the easiest. So normally when we fly robotic missions like this, we send them to a comet or we send them to an asteroid or to Mars, and we never expect that spacecraft to come back. But in this case, we needed to bring the spacecraft back. And so there's a lot of engineering and orbital dynamics that are involved in making that easier to do. And so we wanted an asteroid that was in a good place that would make that easy. And then we also wanted to make sure that the asteroid we picked would have a variety of little rocks and pebbles and sand on its surface for us to sample. If we go to an asteroid that is nothing but big rocks, we can't pick anything up and bring it back. And if we go to an asteroid that has nothing but dust, then we've looked at stuff that's basically been pulverized over time. And so we kind of wanted a Goldilocks asteroid in terms of, the little pieces that we could pick up and that would work with the equipment we have to do the sampling. So the long story short there is that we wanted an asteroid that was larger than 200 meters in diameter. So that eliminated a bunch. And then lastly, we wanted this asteroid to be carbon rich so that we could explore these early organic molecules. And so that list of criteria, believe it or not, brought us to only 5 asteroids that would be good candidates for this mission, and we chose Bennu. And I'll note too that what's also kind of interesting is that simultaneously, the Japanese have been conducting an asteroid sample return mission called Hayabusa 2, and they chose one of the other 5 asteroids for their mission, and that asteroid's called Ryugu. And they'll be returning their sample to Earth this December.
So will you compare notes and see how Bennu compares to the asteroid they're exploring?
Absolutely. In fact, we have team members on their mission and they have team members on our mission. And we're working with them to also exchange samples between the Japanese mission and the US mission. So their samples are going to be a good sneak peek for what we might expect to find from Bennu.
Really neat. So Bennu basically just checked all the right boxes, and that was the destination chosen. So how I know you said that you looked at multiple asteroids and narrowed it down to your top 5, but how do you even go about discovering an asteroid? How was Bennu discovered?
So Bennu in particular was discovered by a project called Linear, and that's all caps LINEAR. And what it means is Lincoln Near Earth Asteroid Research. And so that was a project that is a collaboration between the Air Force, NASA, and MIT to automatically detect and track near Earth objects from ground-based telescopes. And so that project happened to find Bennu in 1999.
So Bennu's been on our radar for over 20 years now, and now it's been chosen to for exploration. So that's really neat. So let's talk about the spacecraft itself. What can you kind of explain what the spacecraft looks like and its capabilities?
Sure. The simplest way to describe it is that, it kind of looks like a box, and then it has 2 big solar panels that stick out on either side, kind of like wings, and they can rotate so that you can point the solar panels at the sun. And we use those solar panels to produce power to charge up batteries that are on the spacecraft. And then the key parts of the spacecraft for doing the mission are a bunch of scientific instruments and then the sampling system. So for science, we have a camera system, we call it OCAMs, and that camera system actually consists of 3 different cameras that are designed to look at Bennu from different distances. And then we also have spectrometers. These are instruments that measure light, not in picture form, but we measure them and record the amount of light that comes into the spectrometer versus the wavelength of light. And so we have a visible near infrared spectrometer called OSIRIS and a thermal spectrometer called OTIS. And these measure the mineralogy of the surface, so what the rocks and minerals are made out of on the surface of Bennu. And then the thermal spectrometer also can measure temperature, and measuring temperature can tell us something about the properties of the rocks on the surface. In addition to those, we have a laser altimeter that we call OLA for making detailed measurements of the shape and the topography of Bennu. If we're going to go collect a sample, we need to have a really, really detailed understanding of where all the bumps and valleys are so that we don't crash our spacecraft. So our laser altimeter does that work for us. And then there's also a student experiment that's produced by MIT and Harvard called REXIS, and that spectrometer measures elemental composition. So those are the primary science instruments that we have. And then we have a sampling system, which consists of an arm that unfurls, and has the sampling device, the sampling mechanism on the end of it. We call that the tag SAM, or the touch and go sample acquisition mechanism. Tag SAM is much easier to say. And then there's also the sample return capsule that sits on the body of the spacecraft. So that's kind of the majority of the systems.
So, a lot of instrumentation there. It sounds like a really advanced system. So, it hasn't collected the sample yet, but have you made any discoveries so far and any surprises yet from the mission?
Yeah, we've actually discovered a fair number of things and had a fair number of surprises along the way. So, our first surprise was when we first got there. We had gone to Bennu thinking from our modeling and our existing observations from Earth that most of the rocks on Bennu would be a few centimeters in size, of up to a couple of inches maybe. But we got there and we just saw nothing but enormous boulders everywhere. And we were really, some folks were really quite shocked. And it turns out that the models that we were using to predict the sizes of the rocks made some assumptions about how porous the rocks are. And it turns out that was wrong. And so when you take so the first surprise and discovery at the same time was that the rocks on Bennu are a lot less dense. They're more porous than we thought they were. We also saw particles being ejected from the surface of the asteroid. So Bennu is an active object. And that really astonished us. We did not expect to see that. We thought maybe there will be a little tiny moon or two around Bennu. That's one of the reasons we have this camera for looking at Bennu from literally thousands and thousands of kilometers away, was so that we could try to look before we got there and see if there was a little moon or something, 14, 15 centimeters in size. But when we got up close, we realized that every few days, there were little particles 1 to 4 inches in size being spewed off the surface, and most of those fall back, but a few escape. And so we didn't expect to see that. We also found some really small boulders, just a few here and there, a couple meters in size, 6, 7 feet. And those boulders don't match the composition of the rest of Bennu. But what's really neat is that they look like the data we get from meteorites that come from the asteroid Vesta. This is it's the largest asteroid in the solar system. And so that was a little surprising in that we know that, or expect, meteorites to fall on objects other than the Earth. Meteorites and asteroids aren't just like magnetically drawn to Earth. Meteorites can fall on any planetary object because these things are, all moving around. But what we didn't expect was to see something that we could really point to where it came from. So that was also a real fun, exciting surprise.
Okay, so but the big moment is coming up. I mean, all these discoveries are big wow moments, but now an even bigger moment is approaching next month. That's the big sample collection. So
Mm-hmm.
tell us about the sample collection. How will it be conducted? And we've already touched on what you hope to learn from it, but if you could kind of walk us through how you'll get that sample back and how you will research it.
Sure. So I mentioned a few minutes ago that part of the sampling system is called tag SAM. So again, we don't actually land on Bennu, we just touch it and go. And so we call the touch and go sample acquisition mechanism. And so this is a container that's at the end of a robotic arm. And so we will fly the spacecraft down towards the surface of Bennu. That sampling head will very briefly contact the surface, just sort of kiss it. And at the same time, we have a canister of compressed nitrogen gas. And that canister will be opened up and that gas will be released very quickly. And that will disrupt the grains of rock on the surface and cause, whatever dust and sand and small pebbles are there to be captured by the sampling head. So the biggest thing we can collect is a little smaller than an inch in size, about 2 centimeters. So then we back the spacecraft away, and while we still have that arm extended, we gently spin the spacecraft and measure the change in the moment of inertia, and that helps us detect that we've successfully collected a sample. And then after that, the arm puts the sampling head into the sample return capsule. The capsule closes up, and then everything is safe. The cargo is contained. And then we leave Bennu next spring for the journey back to Earth. And then in the fall of 2023, we come close to the Earth. The spacecraft is pointed directly at the Earth. We will release that sample return capsule. And then as the sample return capsule continues to fly straight towards the Earth, we'll divert the spacecraft so that it doesn't crash into the Earth right behind the sample. The sample return capsule continues on. It comes down through the atmosphere, and it will land in the Utah desert. And we have a crew of the team members who will go and recover it. They will not be opening it or doing anything with it at that time. They'll document everything, they'll take pictures of everything, but then they'll load that capsule up and it will get transported to NASA's Johnson Space Center in Houston. And that's where all of our lunar samples are kept, and that's where a lot of meteorite samples are kept. So they're used to curating these very valuable kinds of samples, and that's where we will do the opening of the capsule and the preliminary analysis. And then after that happens, everything gets cataloged. Everything we collected will get cataloged, and then eventually part of that sample will be made available to the scientific community all over the world for analysis. Most of the sample will actually be protected and archived for future generations to study, just the way we've done with the lunar samples. And so then any scientist with any kind of instrumentation will be able to request pieces of our return sample to do scientific analysis on. And of course, the science team on the mission will also be doing those kinds of analyses as well.
So the spacecraft is just going to whiz by Earth, drop off the sample, and keep moving. Is that correct?
Yep, that's exactly it.
Where does the spacecraft go?
Well, that's sort of an open question right now. I mean, right now we have no definitive plan to do anything else with it. It will go into orbit around the sun. The instruments, we hope, will still be functional after the sampling event. It's possible that they might get damaged if, rocks and things come back and hit the spacecraft or hit the instruments, but we don't think that will happen. But, you never know till you try it. But it's always possible that NASA might decide, that if there's somewhere else we could take this spacecraft and do some valuable science, maybe we'll get an opportunity to do that. Who knows?
Oh, really neat. So, what is the space? I was reading that there's like a rehearsal for the sample collection, and
Yeah.
how is the spacecraft and the team back here on Earth preparing for the big moment of the sample collection?
Yeah, so this is the first time an operation like this has ever been attempted. And so we wanted to make sure that we understood very, very well how the spacecraft was responding to commands, how it was reacting in the environment around Bennu. And so we've now had 2 rehearsals that help us understand those things, and they've both gone beautifully. So the navigation team and the spacecraft teams are really, really confident that we're going to have a successful sampling. But it really was fun because we got to turn on the instruments that will be on during the sampling. And I think at our closest approach the last time, we got within about 11 meters, I think, of the surface of Bennu before we backed away. We didn't complete the sampling, of course, but we came really, really close. And so that's been a lot of fun to see. And I think it's made everybody really excited for the actual event.
What impact could this have on humankind? I mean, as you mentioned, there are a lot of firsts here, and this is a really big deal.
Yeah, so I think there's a few different ways this mission can will impact humankind. So I think, to the first answer needs to be about what does the average person on the street care about? And so the thing that is probably most relevant to the daily lives of people is what we can learn about the hazards that asteroids in Earth crossing orbits pose to us. So there've been instances in the news even just a week or two ago from when we're talking about small asteroids that whiz by the Earth, and how we don't even know some of them are there until very shortly before they fly by or they actually impact. And even if they burn up in the atmosphere, someday one might not. And there was an impact called Chelyabinsk in Russia a few years ago now that was really quite dramatic, and nobody was expecting it. And if a particularly large asteroid hit the Earth, that could be very, very damaging. So the data that we're collecting at Bennu help us understand how the orbits of asteroids change over time, because they do. They're not the same. And so part of the uncertainty in whether we're going to get hit by any given asteroid is just not knowing if its orbit is going to stay the same and continue to pose a hazard to us. So we're trying to help educate the science community with our data about how we can better predict which asteroids may become hazardous or less hazardous over time. So that's one thing. The other thing is really the detailed science that's going to come out of these return samples. And that's something that the average person may not really hear about very much unless we make, some tremendous discovery that really makes news. But we talked about the need for uncontaminated samples before. And so there are things we're really still trying to understand about the early solar system, like what the organic chemistry was at that time and where things were in the solar system. We know that these asteroids have moved around in the solar system. Just because they're crossing the Earth's orbit today doesn't mean they didn't used to be further out in the solar system at some time in the past. And so we're trying to understand where things were, how they've moved around, what was the chemistry that was going on at that time, where was the water, what was its composition, because there are details about the composition of water. Most people, might not realize that. And so if we really understand better these things that were going on at that point in time, that ultimately helps us better understand how things evolved to where we are today, where we have life on this planet, and helps us understand about solar systems in general that might exist in our galaxy or other galaxies in the universe. And it just helps us learn about our own origins.
Most of us don't realize that these really small objects in space would hold so much information or potential information that could, bring us some great insight into our origins. So that's really neat. I'm just kind of taken aback with everything you're learning about, or you're teaching us today about asteroids. So, and I have to ask, as you mentioned, there has been a particular asteroid in the news lately that is projected to come close to Earth in early November. Asteroid 2018 VP1. Are you keeping tabs on that one?
Well, I know a tiny little bit about it. I should explain, too, that I'm a planetary geologist, so I'm not an astronomer by training. So, watching asteroids and all that is really not, in my wheelhouse. But I know about a little bit about this object. Fortunately, it's pretty small. It's only a few feet across. So the predictions are that it's got a 1 in 240 chance of hitting the Earth, which are, that's pretty good odds. But it's so small that it will probably mostly break up in our atmosphere if it does impact the Earth. And maybe we'll get some smaller pebble-sized meteorites out of it that survive that and land on Earth. But the good news is I don't think it's something we need to worry too much about, from a hazards perspective.
Yeah, I had to ask you about that. I couldn't pass up the opportunity to get your insight and perspective on it. So Thanks for chiming in on that one. But, of course, back to OSIRIS-REx and Bennu now. What has been the biggest breakthrough moment so far? I know the sample collection will be huge, and that will probably be top of your list soon enough. But, if you can name a biggest breakthrough moment, what would it be?
I honestly have to say it's hard to say that there's only been one. And I think too, different people on the team would give you different answers. I think that generally speaking, among the biggest surprises have been these particle ejection events. That really wasn't something we were expecting, and to see this and potentially suspect that maybe this is a process that's much more widespread than we ever realized. This might be happening at all asteroids or some large fraction of them, and we've just never been close enough to see it. It is a pretty big breakthrough. And I think, yeah, that after that, I think maybe the just the fact that we saw so many large boulders and realized that some of the assumptions we were using in our models were maybe not right was a really educational moment. But yeah, I think, undoubtedly when we have a sample collection that's successful, that's going to be huge. That's technological and scientific breakthrough.
So you say your official title or your area of expertise, planetary geology, is that correct?
Yes.
How did you focus on that particular field? How did you choose this as a career path?
I would say it was a series of happy accidents. I never thought I would be a scientist. As a kid, I was always, and as a student, I was always much better at, English and social studies and history, those kinds of fields. Math and science was not, what interested me. I'll confess that I'm actually horrible at math. But I took a geology class my first year in college and fell in love with it. And I love geology because you can literally walk around outside and it's everywhere, it's all around you. And to be able to look at a mountain range and understand something about how it formed, or the fact that there are different kinds of rivers and why different rivers look different, or why earthquakes happen, or how volcanoes work. I mean, I just found that all fascinating. And then when I decided to change and become a geologist, I had an opportunity to work at NASA's Jet Propulsion Laboratory in Los Angeles because that's where I was going to school. And I got to be an intern on a NASA mission called Magellan, which was at the time exploring Venus. And I got to work with the scientists there and see these images of Venus coming back and realize that I was one of the first few dozen people on planet Earth to see these pictures of another planet. And I literally said, people get paid to do this. And so that was when it happened. And then I decided, yeah, this is what I want to do. And so I went to graduate school and here I am.
Women are traditionally underrepresented in science and technology fields, but here you are in such an incredible role. Do you have any words of advice for little girls who are dreaming of exploring space and being just like you when they grow up?
I think my best words would be don't give up. Don't let anybody tell you you can't do it. I just confessed that, I don't particularly enjoy math. I'm not particularly good at it. And yet here I am. I found a field that, helps, that enables me to do this without having to, be great, at math or at physics or whatever. And there are a lot of different ways you can be involved in exploring space. You could be a scientist like me. You could, be chemist or physicist or, biologist or whatever. You could be an engineer, if that's interesting. But you could also be a software engineer. You can write the software that runs these instruments or collects, helps process the data that the scientists are looking at. Or, we have accountants on our team. They're crucial to doing what we do. We need somebody who, worries about the budgets and sends the money to the scientists and to the engineers to build the spacecraft and do the science and all of that. And so there are a lot of ways to be involved in exploring space. You don't have to be a scientist or an engineer to do that. And I think that's really important too. But yeah, I mean, if you do want to be a scientist or an engineer, go for it and just, keep chipping away at it, and find good mentors is also a really valuable thing. I've been so fortunate to have some really good mentors throughout my scientific education and career, and that too is a really important factor. But I for me, I kind of go back to a thing I'll paraphrase from Carl Sagan. There's stuff out there that's waiting to be known, and we can be a part of that. Women can be a part of that and should be a part of that. And I just think that's, incredibly important to encourage.
I love that advice. Let's all strive to be a part of that. Perfect. Well, we are so excited about this sample collection, and we will be holding our breath for 3 years to see what Bennu is holding. So we can't wait to find out what you and your team discover. And so thank you for joining us today, Vicky, and for this really great, in-depth, inside perspective on OSIRIS-REx. It's, as I said, certainly an exciting time.
Thank you so much. I've really enjoyed talking with you.
And that wraps up this episode of Technology Today. Subscribe to the Technology Today podcast to hear in-depth conversations with people like Vicky, changing our world and beyond through science, engineering, research, and technology. Connect with Southwest Research Institute on Facebook, Instagram, Twitter, LinkedIn, and YouTube. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SwRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host Lisa Pena. Thanks for listening.